Hi everyone, myself Saranya, working as an assistant professor in the Department of ECE at Sri Shanmugha College of Engineering and Technology. Today I'm going to discuss about the scattering parameters. In previous video, I discussed about the basics of microwave engineering and general elements present in the microwave system. In this session, today I'm going to discuss about scattering parameters, why we are using the scattering parameters in the microwave frequency ranges. So this is the today outline of the presentation, scattering parameters and then microwave vacuum tubes. So definition. So why we go for scattering parameters? So in generally in low frequency ranges, we are going to measure the power levels in terms of voltage and current. But here in microwave frequency ranges, we are going to measure only the total power, that is P is equal to V into I. So here in microwave frequency ranges, we are going to use only the high frequency ranges, that is from 300 megahertz to some few 300 gigahertz. But in low frequency ranges, we are going to utilize only the frequency ranges up to some few kilohertz, that is 300 megahertz, below 300 megahertz. So here, when compared to low frequency and high frequency, for calculating the power calculations and for measuring the voltage and current relations, there is a separate parameters for calculating the voltage and current values. In low level frequency ranges, we are going to calculate the voltage and current level by using the parameters like Z parameter, Y parameter and then ABCD parameters, etc. But when compared to the when coming to the high frequency ranges, for calculating the entire power level of the microwave system, we need S parameter calculations. That is called as scattering parameters. So scattering parameters is mainly used for the calculating the power levels between the incident, that is from the source and destination, that is how the incident power waves are at ports are reflected and then transmitted from the input side. So here we are going to calculate the power level, that is P is equal to V into I. So for measuring the high frequency ranges, so the parameter is nothing but scattering parameters. So in terms of scattering parameters, here we are going to calculate the voltage and current value and then corresponding power levels at the certain elements of the microwave system. Next one, need for scattering parameters. So why we go for, what is the need of the scattering parameters means? So already I discussed, that is voltage and currents are very hard to measure at microwave frequency, because due to the frequency ranges, it is very difficult to measure in terms of Z parameter and then Y parameter and then ABCD parameter. So that is applicable only to low frequency ranges. So when we come to the optical frequency ranges, that is high frequency ranges, this is the parameter for measuring the power calculations. That is, power calculation means it comes under voltage and current relations. So at microwave frequencies, mainly if once the frequency range is high, the wavelength is very short. So at that time, voltage and current level are very difficult to measure in the microwave frequencies. So we are using the scattering parameters. So separately we are using the instrument like as VNA, that is vector network analyzer. By using the vector network analyzer, generally we are going to measure the transmission coefficient and then reflection coefficients of the scattering parameters. That is the main purpose of the VNA device. And next one, based on the number of ports present in the microwave components, we can calculate the separate S parameters for the devices, microwave devices, based on the n number of ports. For example, in previous slide I discussed about isolator components and then circulator components. So in general, isolator is a two-port device. So for two-port device, S parameter calculation is different. And for three-port device, for example, circulator is a three-port device. So for calculating the power level in the circulator, we need to use 3x3 matrix for the power calculation in the microwave system. And similarly, in directional coupler, we are using 4-port devices in general. So for 4-port devices, we are using 4x4 S matrix calculation. By using this calculation, we need to calculate the entire power level of the microwave system. So based on the n number of devices, that is n number of ports, based on the components present in the microwave system, we are going to analyze the scattering matrix for the entire power analysis in the microwave system. This is the main concept of the scattering parameters. For example, here we are considering n port of devices. So I discussed, based on the number of ports, we can utilize the scattering parameters elements in the microwave system. So for example, consider this is the general S matrix of the microwave system. So this is V1, V2 up to n number of ports, and S11, SNN is nothing but scattering parameters. In terms of S matrix, in terms of matrix form, we are calculating the power levels of the microwave system. And next one here also we are going to consider the voltage level. So this is the general S parameter matrix for the representation of the microwave system. So consider if already I said that for isolator is nothing but two port device. So consider the two port devices, that is for consider the two port device, we can calculate the S parameter means we can write the equation as V1 V2 is equal to S11 S12 S21 and then S22. If it is three port network, we are going to assume the element as that is n cross n. So n cross n means based on the number of ports, we are using the 3 cross 3 matrix and then 4 cross 4 matrix. So based on the n number of ports, we can calculate the power levels present in the microwave system. And next, this is the microwave vacuum tubes. So due to the high frequency ranges, for calculating the power levels, we need the vacuum tubes. That is, for low level frequency ranges, conventional tubes is essential. But in microwave frequencies, the conventional tubes are not applicable to calculate the power levels present in the microwave frequency. So this is the main drawbacks in the microwave frequency ranges. So that's why we are using separately, we are using microwave vacuum tubes for the devices, microwave systems. So generally microwave tubes can generate and it will amplify the microwave signals and it generates the high power level at the output system. So in general, compared to the low frequency ranges, the microwave frequency generates always the high power microwave system which effectively with the efficiency is better when compared to the low frequency ranges. So these are all the general applications we are using in the microwave systems, that is radar system, satellite systems, space communication, microwave transmitters, and then particle accelerators. So what are all the general vacuum tubes we are using in the microwave system means that is reflux klystron. So reflux klystron is the main element present in the main source of the element present in the entire microwave system. So next one, types of microwave tubes. There are two types of microwave tubes. One is linear beam tubes and then cross-field tubes. So linear beam tubes is nothing but O-type tube and it is denoted as O, and cross-field is denoted as M-type. So under the linear tubes, these are all the linear beam tubes we are using in the microwave system. First one, klystron. So under klystron, it is again splitted into types, that is nothing but reflux klystron, and the next one TWT is nothing but traveling wave tube. So these are all the three microwave tubes which present in the linear type, and the next one cross field tube is nothing but magnetron, amplitron, and then dematron. So mostly in application side we are using only the magnetron type of cross field tubes in the microwave system. In linear beam tubes, mostly we are using all the three types of linear beam tubes in the microwave system. The main source is reflux klystron. In previous video, I posted about I already discussed about the entire block diagram of the microwave system. In that, I mentioned that the reflux klystron. So linear tubes. So what is mean by linear tube means generally in linear tubes the electron beam travels only in the straight line. So at that time the electric field is parallel to the direction of the electron motion. So this is nothing but linear tube. Here it is in parallel direction and in cross field it is in perpendicular direction. That is the difference between the linear tube and then cross field tube. So this is the general characteristics. So main characteristics is the electron moves from linearly from cathode to anode, that is cathode to collector terminal. Here the electric and magnetic fields are always parallel, and the mainly we are used in the microwave amplification process. Mostly we are using the reflex klystron oscillator like that. Mainly we are using the linear beam types of tubes in the microwave system. And these are all the few linear types, that is klystron, reflex klystron, TWT, and then another one is inductive output tube. So mainly we are covering only these three types of tubes in the general amplification process and as well as in the oscillator process of the microwave system. So these are all the main applications of the linear beams, that is radar transmitter in general, satellite communication and the television broadcasting. We are using all these in these sectors we are using only the linear beam tubes of the microwave system. And next one, cross field tubes. So this is the cross field tube. So in previous slide, I discussed about the linear. Here, cross field means the electric field and magnetic field are perpendicular to each other. In linear tube, it is in parallel to each other. In cross field, it is perpendicular to each other. So at that time, the electrons moves in the curved path. So at that time, we can utilize in the applications like magnetron. So for in real time, in next slide, I discussed about the one of the real time applications of the magnetron. Normally, we are using in the home appliances. So these are all the key characteristics of the cross field tubes. Here, the electron motion is based only on the spiral or then circular. So based on the curved path, and normally the electric field and magnetic field are perpendicular to each other. So at that time, it will be rotate in the either circular or the spiral path. So that's why this is the main characteristics of the cross field tube. So E field is perpendicular to the magnetic field. So mainly we are using only in the microwave generation. So these are all the few types of the cross field tubes, that is magnetron, cross field amplifier, amplitron and then planetron. So these are all the types of cross field tube and applications. We are focusing only on the microwave ovens and also the radar system and industrial purpose. For heating purpose, we are using the cross field tube. So based on the applications and based on the frequency ranges, we can choose either the linear types of tubes or as well as the cross field tubes. It is depends on the application side, and then frequency is also very important of the microwave tubes. So this is the example for the linear tubes and then cross-field tubes. So this is the general constructions of the linear beam tubes and then cross-field tubes. So this is the sample reflex klystron I showed here. So this is the reflex klystron source. This is the main source of the microwave system. So at the input side, we are using only the reflex klystron. It acts as either amplification or as an oscillator purpose. We are using the reflex klystron components, that is main act as the source. So at that time, the linear means the electron which travels only in the parallel path, that is it travels in the straight line. But in cross field tube, the electron is travels in circular path, that is the electric field is perpendicular to the magnetic field. So at that time, the electron takes place moves in the curved path. So we are using the magnetron type of cross field tube in the real time applications. So this is the general types of linear tubes. So types is, so under linear beam tubes, one is klystron tubes, hybrid tubes and then traveling wave tubes. So in klystron, it is again splitted into two types. One is two cavity klystron and then multi cavity klystron. So based on the frequency ranges, we can choose the cavity, n number of cavity. So that's why here under the klystron tubes, it is classified into two parts. And again from the klystron tubes, it is again splitted into two parts. One is reflex klystron and then ladder turn. And next one, hybrid tubes. It is nothing but klystron. And under traveling wave tube, it is again splitted into helix ring traveling wave tube and then helix backward wave oscilloscope or oscillators and then coupled cavity TWT. So these are all the main general types of the linear beam tubes. Next one, traveling wave tubes. So when it comes to the traveling wave tube, it is nothing but the slow wave structures. In general, we are using based on the frequency ranges, the traveling wave tubes will be considered, that is TWT. So mainly the frequency range of the traveling wave tube is, it is starting from 300 megahertz to up to 50 gigahertz. We are utilizing in the traveling wave tubes of measurements in the general microwave applications. So it is nothing but it is a non-resonant circuit. It will propagate only in the helical line. The electrons will take place in the helical line structure. So that's why it is mentioned traveling wave tubes. So it is also called as slow wave structures. So compared to the reflex klystron, it provides high output power when compared to the klystron. So the maximum gain of the traveling wave tube is up to 40 decibels we can utilize in the traveling wave tube. So with low noise, and we always generate the high power output, and based on the frequency ranges the bandwidth also very high in the traveling wave tubes. So these are the types of slow wave structures. First one, helical line, folded back line, zigzag line, interdigital line, and corrugated waveguide. So mostly we are using, in previous slide itself I discussed that mostly we are using only the helical type of slow wave structure. Based on the frequency ranges, it will generate high power in helical line. When compared to the remaining types of slow wave structures, it will generate better decibels. It provide better power levels, that is up to 40 dB. Next one, magnetron. So magnetron I discussed previously. So it is one of the high power vacuum tube. It generates the electromagnetic radiation based on the interaction of the electrons which are present in the entire magnetron system. And normally we are using the resonant cavity present in the entire structure. So normally in general in magnetron we can utilize the frequency range up to from starting from 300 megahertz to only 10 gigahertz. So mostly it is enough for the commercial applications. So they designed the frequency range up to only the 10 gigahertz frequency. It's enough for the magnetron application purpose. So magnetrons, it is nothing but cross field tube. Here the electrons will take place, that is electric field is perpendicular to the magnetic field. So due to this the electron will travel in the circular path as well as in the spiral path. So at that time we will generate the high power oscillators, and we can also utilize in the applications of radar applications, and also in microwave heating, and as well as in the microwave ovens also we are using only the magnetron type of tubes. And these are all the types of magnetron, that is split anode and cyclotron frequency magnetron, and then traveling wave, or it is nothing but cavity. So based on the frequency ranges, it is split into three levels. So here first type, it is operated only less than 500 megahertz, and then cyclotron type frequency, it is operated that is higher than 100 megahertz. But in cavity type, we can use the gigahertz frequency. That's why I mentioned, I discussed, mostly we are using 10 gigahertz up to the 10 gigahertz frequency. So split anode and then cyclotron frequency magnetron operates only under the megahertz frequency, and then traveling wave and then cavity magnetron, it operates in the gigahertz frequency, that is high frequency. It comes under low frequency, but compared to the low frequency, it provides high power level at the entire microwave system. So we are using the cavity magnetron types in practical applications. So this is the applications. So in general, we are using the TWT in the satellite communications and as well as the radar systems. So this is the TWT structure. So based on the n number of ports and based on the vacuum tubes, we can utilize the amplifications of the signal which present in the entire microwave system. So in previously I discussed that frequency range is maximum starting from 300 megahertz to up to 50 gigahertz. So it covers the entire frequency ranges. It is maximum. It is enough for the radar system applications and as well as for the satellite communications. And this is the general constructions of the magnetron, structure of the magnetron. So this is the entire magnetron. So in I discussed about that is in magnetron is a device. It is mainly it provides the high microwave power level at the output system. So mainly magnetron in commercial applications we are using in home appliances, that is in microwave ovens. So consider, so this is the consider this a microwave oven. Here we are using the waveguide. So in basic first previous video I discussed about the waveguide. So once for transmitting the electromagnetic signal without waveguide we can't able to transmit the signal from source to destination because it is a high frequency ranges. So due to the high frequency ranges we can able to transmit only the waveguide. So by using the waveguide only we can able to transmit the microwave signal. So it is nothing but a hollow metallic tube. It is mainly designed only for the transmission of electromagnetic signal. So that's why we are using the waveguide inside the elements, that is, and here this is magnetron. So magnetron, there are different types of magnetron. Here we are using the cavity magnetron, that is nothing but cylindrical type of magnetron. So in cylindrical type of magnetron, in microwave oven we are using only the cylindrical type of magnetron. So in general, magnetron is magnetron, the electric field is perpendicular to the magnetic field. So at that time the electron will travels in the curved path or then circular path or as well as in the spiral path. So that here the magnetron we are using the cylindrical path, cylindrical magnetron type we are using in the microwave oven, and it is nothing but fan, and this is we are using the power supply, and this is nothing but tunable and then base plate of the microwave oven. So these are all the main microwave elements we are using in the microwave oven system. So in general, microwave oven it operates up to 10 gigahertz. So it's the high frequency range level. So microwave generation. So inside the oven, micro magnetron is fixed here. That is for providing the high power level. And next one, microwave transmission. The waves are directed into the food and heating. So microwave causes water molecules in the food. Generally, it automatically generating the heat and cooking the item inside the microwave oven, which present in the microwave oven, and even heating. So here for even heating, here the fan are tunable and the base plate which helps to distribute the entire microwaves unevenly from the uniform of the cooking. So this is the main function of the applications of the magnetron. Normally we are using in the microwave oven. And these are all the general applications we are using in the tubes, microwave oven tubes, that is radar system. In radar system, it provides high power microwave sources. Especially under radar system, we can also utilize for the military radar and then weather radar and also in air traffic control. And generally, we are using for satellite communications and for microwave communication link. It is up to point communication and as well as in the TV and radio relay systems. And magnetron, I discussed about the microwave oven applications, and then medical applications, and then electronic warfare, scientific research, navigation systems. Thank you.